Uh, the, the green text. When you finished.
Stand on the floor will be too high. So you can start. Can you just hush now? Okay. Just sorry. Just okay. Here. This way. It's better this way.
Okay. Thank you, Professor.
What slides now?
Yeah. So let's start.
I don't see anything.
No, I'm starting. Yes, I can say. So good afternoon, everyone. My name is Bishal Nahak, and today I'll be going to present my topic on application of plasma engineering for renewable hydrogen generation as well as for different energy storing devices. So before going to start my presentation, I will talk about how like hydrogen generation and renewable energy has been important in today's life, and how why we are using plasma to increase the efficiency of hydrogen generation, as well as the storage of in many storage devices plasma has been used, and how it can be implemented. And in last, I will talk about what are the current challenges that are being faced in this, and I will provide some conclusions regarding that. So from the figure, we can see like how the main motivation comes from the picture shows that CO2 emission has been increased drastically since last 5 decades, since 1952 until 2021. And from the next figure, we can see like a few of the main major sources that are responsible for CO2 emission is coal and oil, which are fossil fuels. And the next figure shows the how countries' CO2 and emission has been increased gradually since 1952, and it is reached to 50 million ton till 250 million ton till today. And one of the major reason is responsible for that is use of vehicles that liberate harmful gases such as causing greenhouse emissions and all. So we need to think some alternative sources of energy or any alternative technology to provide some energy that is doesn't emit any CO2 emission or causes any greenhouse gases, and which can also provide some better efficiency than commercialized fossil fuels. So the solution could be like currently government has been working on hydrogen energy technology, which has been like currently implemented in several parts of our country. And why they have chosen hydrogen? Because hydrogen is having high calorific value, which is quite more than 3 times of commercialized fossil fuels that are being used till now. And also this hydrogen can be generated in much more renewable way, just using wind, sun, or tidal energy. So for also this hydrogen can be carried to a long distance without using any specialized equipment. They can be just used to pipelines can be used to just transport the large amount of hydrogen from one place to another. Also coming up to energy storing devices, the traditional lithium ion batteries have a problem of charging and discharging, where the hydrogen based fuel cells or energy storage devices can also increase the efficiency as well as they solve the problem of self discharging. So
Use the laser phone and use your mouse. The laser phone. You have to
okay, no, I said this. Oh, yeah, first one, yeah, yeah. So yeah, thank you. So the picture shows about how hydrogen can be generated in different ways. It can be mainly classified into 4 different ways, that is green, blue, gray, and brown hydrogen. Whereas the rightmost brown and gray hydrogen are mostly responsible for emitting CO2 gases and harmful gases to the environment. Whereas blue hydrogen provides CO2, but they are being captured after before they are being liberated to atmosphere. In the industrial level only the CO2 gases have been captured. But in case of green hydrogen, there is no emission of any carbon dioxide or any harmful gases, so they are much more renewable, also cost effective compared to other 3 ways. So the picture also, so the in beside we can see there are different commercialized ways where hydrogen can be generated, and those source the in bracket they source about their efficiency, and we can see the steam methane reforming and coal gasification almost contain source around 60 to 70 percentage of efficiency. Whereas coming to the down, we can see the photolysis of water, which is considered to be green hydrogen, and that shows only 10% of hydrogen generation, which can be said like the efficiency is still very low compared to other sources. So how can we increase this source of photolysis of water to increase the generation of hydrogen? So in our main presentation we will be concerning about more green hydrogen. So I will talk about how this part, like this photolysis of water or photocatalytic water splitting, can be enhanced using plasma technology. So these are the few ways from where the hydrogen can be generated. But as I said, like we are more concerned about like a more renewable way to generate hydrogen, and so we can just sort it down to some renewable ways. That is using heat or biomass to that can be converted into that can be converted into mechanical or electrical, and some process interconversion can be done to convert it into green hydrogen. And further, this green hydrogen can be applied for different industry or transportation or heating or power generation, such as electricity. So how as I said, like this efficiency has been still now very low, and it contains about 10%. So we need to increase the efficiency, and there are many ways to increase the efficiency. And one of the main way is to increase the efficiency of fuel cells that generate the hydrogen generation. So coming up before going to the how we can increase or how plasma plays an important role in this fuel cells, we have to talk about the basic mechanism that is being involved in the fuel cells. So here yes, here we can see about the in this from the left, the anode hydrogen is being passed to or towards the right, and here the hydrogen liberate electrons, and that electrons is being passed through this, and in this way these electrons are being captured by oxygen, and they are being forming here O2 sorry HO2, that is water, and also the current is being generated in this medium. And here this process occurs in the presence of an electrocatalyst. Here the role of catalyst plays an important role, and here we can say what these are some of the advantages that are being there for fuel cell or the proton exchange membrane based fuel cells, and they are renewable and also provide greater efficiency. And this is the basic mechanism, and where we can see now, like now we can talk about how to increase the efficiency, because we know the basic mechanism that is being followed in the commercialized or in the current fuel cells that is being researched till now. So one of the main role that is being played in this fuel cells is the electrocatalyst, and we have to increase the efficiency of the electrocatalyst to thereby increase the efficiency of hydrogen generation rate. So one of the way to increase the efficiency of the electrocatalyst is to do the surface treatment, and these surface treatments can be done by plasma engineering. So why we are using plasma engineering, and what is plasma? And plasma is the fourth stage of matter, and it consists of free radicals, electrons, and exciter particles, and neutrons and electrons. And when these uh, yeah. When these energetic radicals goes through the any surface or the any surface of the material, they hit to the surface and create many defects or vacancies, which help in react making the material more active, which is more helpful for generating hydrogen generation as well as for oxygen evolution, and different reactions become more faster. And so thereby plasma engineering has been helpful for increasing the efficiency of different photocatalyst or electrocatalyst by increasing the defects or vacancies created by the on the surface or interface of the different materials. So this plasma can be created through different ways. That is, non-thermal can be classified into two different ways: thermal and non-thermal. And the non-thermal, we can see that the electron temperatures can reach up to 10 to 100 K, 100 K, while the gas remain at the room temperature, which is like we need not to use any high temperature to in this case. The high electron temperature makes the non-thermal plasma unusual and prominent. And also in case of thermal, we need to use energy, as well as the heat, the temperature need to be very high. So one of in commercialized tests and also in many different research industries, thermal methods are not being used, and they are normally they use non-thermal ways to generate the plasma. And this non-thermal waste to generate the plasma can be further classified into glow discharge plasma and RF discharge plasma, that is radio frequency discharge plasma, corona discharge plasma, and DVD discharge plasma. For coming up to first, the glow discharge plasma. The discharge plasma could be simply generated by applying high voltage between two electrode. Here we can see, you can see between the two electrode with a broad range of pressure. And in the basic mechanism that is involved in the corona discharge plasma, the corona discharge plasma can be generated by gas breakdown in strong uneven electric field at a atmospheric pressure, and relative current of this plasma should be very low. DVD plasma, dielectric barrier discharge plasma, could be initiated by insulator to stop the electric current in a high voltage electric field with high frequency at a atmospheric pressure, and which is also called a silent discharge plasma. Microplasma, also called as solution-based plasma, can be generated by breaking down the gas layer between the electrode and the liquid with a high voltage up to 30 kilovolt. RF plasma, the radio frequency discharge plasma, is being generated by ionizing the low pressure gas with a high frequencies and by a two generation way, that is inductive discharge and capacitive discharge. And gliding arc discharge plasma, that is GAD plasma, is considered as an innovative technology and being mostly recently used, which offers the features of both thermal and non-thermal plasma. In gliding arc discharge plasma, the high voltage is introduced between two or more in a thin knife edge divergent electrodes. Some of the recent advantages that are being used. Now we will talk about how plasma has been used in the different electrocatalyst synthesis, and how they increase the efficiency of hydrogen generation rate as well as the oxygen evolution rate. Here here in the first figure we can see figure A. Here that is the research is being conducted by Shu, and they report a robust physical spotting strategy to synthesize a defective tungsten carbon layer on a graphene thin. This is a graphene thin film, and they sputter on it to increase the efficiency of the graphene thin film, and thereby they use it for different hydrogen generation application, which significantly they compared with other result, and the result provided very good after using the plasma technology. In the figure B we can see that is being done by Crick and the plasma vapor deposition to deposit platinum, nickel, and aluminum thin films for. And was used thin film was used for oxygen evolution reaction, and this was done in alkaline medium. And the oxygen evolution was quite significant as compared to other literatures because of the use of plasma technology in this part. Further, coming up to figure C, in the figure C shows about the TiO2 nanotubes, and where depositor like the diamond like in the shape of carbon has been deposited on the TiO2 nanotube, and the AgTiO2 nanotubes as electrode here was used for the HER generation, that is hydrogen evolution reaction. And this figure D shows the molybdenum oxide, that is a metal oxide oxide, which used to host the grown conductive glass. And this, like on a conductive glass, this molybdenum oxide was grown, and this was being done by CVD, plasma assisted, that is plasma assisted CVD, chemical vapor deposition. And subsequently the AU, that is gold nanoparticles, was used to functionalize these conducting wafers, and they further use it for HER generation. And now coming up to how plasma can create some defects, and there are different defects that are present in a material surface, and those can be categorized into 0-dimensional, 1-dimensional, 2-dimensional, or 3-dimensional. The plasma helps with a high controllability to produce a consistent vacancies and defects. And in this slide I will talk about 0-dimensional defects. Here in the first figure A, we can see how it was done by Liu, which was adapted, in which they have adapted a nitrogen plasma etching to create a abundant and also a uniformly distributed defect and vacancy sites on the NiMnO4, that is nickel molybdenum oxide array surfaces, followed by which they created some defects, and these defects are being further fulfilled by iron and platinum nanoparticles, which they helped in increasing the hydrogen generation. And also further coming up to the next slide, no, sorry, next research that is being done by Wang, where they have used oxygen plasma to control the formation of to control the formation of tungsten vacancies on tungsten tellurium nanoseeds, which they gave like feather-like structure, and this feather-like structure also helps to reduce the charge carrier recombination, and also they thereby charge carrier recombination also plays an important role in hydrogen generation. Due to decrease in the rate of charge carrier recombination, the hydrogen generation has been also increased significantly. In the last picture we can see the graphene nanoseeds with doped nitrogen atoms with RF, that is radio frequency nitrogen to plasma was used, and the ultra small iridium nanoparticles were sputtered on it, and this was further used to generate the oxygen from this material. And now we will talk about 1-dimensional or 2-dimensional based defects that are being followed. And this this research is being conducted by Q, where they have used NiO, nickel oxide, nickel oxide semiconductors, and they try to create different delta-like structure, or we can say Iceland-like structure, using plasma technology, where the plasma was used, DBD plasma was used, and they further use it for both like HER as well as OER, and like this NiO based catalyst showed both type of reaction, that is, and can be used for hydrogen generation as well as oxygen evolution reaction. Coming up to the B figure shows the Q, which was adapted in the solution based plasma, and they used a magazine, 2-dimensional magazine layers and these magazine layers were supported by platinum and palladium, where they used further this palladium and platinum based magazine structures were used for different hydrogen and also oxygen evolution reaction. And the figure C, we can see the argon plasma to is the MOES2 nanoseeds, where they used for again HER and OER evolution. From this slide we can say like the plasma that produce 1-dimensional and 2-dimensional structures, sorry, 2-dimensional defects, and this catalyst can be used for both of the reaction, for hydrogen generation as well as for oxygen evolution. Whereas in our last slide we talked about the 0-dimensional defects that are being caused due to plasma as only used for oxygen hydrogen generation reactions. Coming up to 3-dimensional that are defects that are caused due to plasma. Here, Here we can see about the Peng, in this figure we can see then the researcher named Peng who employed a solution plasma reduction to construct a metal nanoparticles that attract the function of the carbon sites, and these catalysts were composed of nickel and ruthenium alloy nanoparticles that enriched in the carbon nanotubes. And further, it was used for HER and OER evolution reaction. In the figure B, we can see about the palladium doping combined with low temperature radio frequency plasma reduction to construct heterostructure of palladium dope NiFe or Fe LDH nanoseeds, and which has rich in oxygen and nitrogen vacancies, and these vacancies helps in increasing the efficiency further. Now we will talk about apart from creating defense deficiency, how this plasma etching can increase the surface area. This surface area can be increased the plasma assisted etching is suitable for creating more edges that are active, and these active sites act as a source of many reactions, and these active sites become more or available towards the hydrogen and oxygen evolution in these areas. Also, the plasma doping on the electronic structure has tuning electronic structure. Here we can here it talks about how plasma doping of any element on any material or any structure can increase its electronic properties or also alters the physical and chemical bonding of the material. Now we will talk about the relationship or the defects on the surface defects, and this how the surface defects can increase the catalytic activity. Now we will talk about it, and here we talked about many things electrocatalytic reactions, and all these reactions occur at the surface and interface of the electrocatalyst, and these structural defects that are caused due to the plasma can facilitate to many activations, absorption, and chemical reaction, and many different types of reaction can be occurred in these active sites. Further, the main role that are being played by this effective defects of the electrocatalyst can be summarized below, and here we can see the atoms that are nearer to the surface of the electrocatalyst will be more available for the reaction, where and this can be seen in the case of here where the Fe and Pt heteroatom was doped in nickel and MnO4 nanoseeds, where the Fe and Pt heteroatom has a dominant actual active sites in the nearer region, and they act as a source of absorption, and different reaction kinetics occurred in those areas. When these different further coming up to next point, the defects such as vacancies and dopings that we talked about and hetero junctions that are formed due to plasma can also form with the electrocatalyst surface, and these electrons can get redistributed according to the environment. Like this point talks about by using plasma technology, it also it not only creates the active site, it also changes the electronic and various physical and chemical properties of the material, and this the material property, for example we can see when plasma sputter tungsten carbon and vacancies were created in the tungsten carbon seeds, and the d band structure similar to that the pt electrocatalyst, and leading to a gives absorption energy, and this raises the hydrogen generation, and similar to the pt, that is platinum in acidic HER process. The defects with higher energy tend to absorb heterogeneous atoms and molecules and groups to stabilize the structure. Afterward, the surface of the electrocatalyst undergoes reconstruction and dynamic evolution of new sites and activation centers. This point talk about how these defects also get after the plasma liberation on any material. These defects are with higher, and they have a surrounding materials and around these defects and have higher energy and tend to react with the surrounding material to adjust themselves, and also to the reaction also increases in those defective areas, and thereby they also increase the efficiency of many reactions such as hydrogen, or it can be also applied for the oxygen. These are the different kind of defects that I talked about. Like these here we can see these are three-dimensional defects, that are atoms. There is no atoms present in this material surface, and these vacancies can be called as zero-dimensional defects. And this layer, when a layer of a material is being not present on a material, it causes like two-dimensional defects. And this like in a single row of a material is not there, or any atoms are not there, this cause one-dimensional defects. Further, coming up to how plasma can also increase the present lithium-ion based technology batteries, we can see like in current lithium-ion batteries have advantages of high energy density and also high output power and long life. However, they suffer of high cost. That is, the current lithium-ion batteries have a high cost as well as insecurity. Like we have seen many cases where lithium-ion batteries get heated up and they get burned. So, how the plasma technology can enhance this or solve this problem? When we consider, or when we talk about lithium-ion batteries, we consider about the anode materials that are being most important part in those batteries. When the lithium is used as anode material, it reacts with the electrolyte to charge and discharge the process, which lead to the insecurity. And because when it is being used for a long time, it get more heated up, and those heating pro issues can cause, and also it may lead to blasting the batteries. So mostly the transition metal oxide like group 4 or group B valence metals are being used to in these areas, where because they have a high energy density. However, the low conductivity of this group 4 and group 5 elements and poor kinetics of these materials causes serious volume charge occur and during the discharge of the cycle. That is, the battery gets swollen up due to their low conductivity and due to poor kinetics. So this can be solved by surface treatment of these materials using plasma technology, and the surface of the materials can be changed by super hydrophobic or hydrophilic by treating oxygen plasma treatment on the certain condition. Like for example, here we can see the Lanital reported successful doping of nitrogen and oxygen nitrogen ions into the oxygen sites in lithium titanate through argon nitrogen plasma irradiation at atmospheric pressure. And further, by doping nitrogen atoms to the lattice get expanded, and thereby they facilitate the lithium mobility. Further, they improve the electrochemical performance. The obtained materials also show the higher capacity of 132, which was earlier 100, and the excellent stability with almost no capacity decay over 100 cycles and under C. The current technology that the current problems that are being faced in this plasma technology are in this the plasma produce various structural defects, and also the size and location concentration and the distribution of such defects, which has seriously affect the catalyst performance, are not easy to control. Like when we use any plasma source to create some surface defects on a electrocatalyst, it cannot be controlled way. Like we can just control the amount of plasma that we are putting on it, but it cannot control the amount of creation of activation site. It may create some large amount of activation sites, it may create some small, or it may also destroy the whole property of the electrocatalyst. So the next problem rise, like the plasma technologies involve high cost and energy conversion, energy consumption. And second, the third point involves like the since two or more plasma derived effects defects such as sputtering, itching, and deposition heteroatoms and more pronounced to consent, it is necessary to design new types of plasma reactors. Like two or more plasma technologies can be implemented in a single way, and this one of the challenge that is being faced. And new in situ characterization method can be developed to track the dynamic and structural evolution of the active sites and of the changing catalyst. Like new characterization can be implemented, which can provide instant, or we can say the real time, what happening in the real timing and real time, like how these activist sites are created and all in on the electrocatalyst can. So a new characterization method can be evolved or researched for that. In conclusion, I can say like the plasma has been used like in many areas for the hydrogen generation as well as oxygen evolution reaction. By and they also the efficiency has been significantly increased, because they create some surface defects, and also they create some vacancies and different kind of heterojunctions, which they further which leads to creation of many active sites, and these active sites reacts with the surrounding, and this they providing much better catalytic efficiency. And further, this surface plasma modifications offers unique advantages in the material for the modification, for such as I talked about high efficiency and rapid preparation, strong versatility, and little environmental effect. Like this plasma technology doesn't affect the current environment much. So it is one of the way to increase the efficiency of present fuel cells that are being commercialized or researched in various institutions. So these are some of the references that I talked about, and these are all review articles, and these review articles I reviewed in my presentation. And thank you for listening, and if you have any questions, I would be happy to answer. Yeah, please.
Okay, in the challenges, you explained that when there is surface defect,
Mm-hmm.
okay, so that is a problem for the catalysis. But if we do not have the surface defects, because we are doing using plasma because we want those defects.
Yes.
Because those defects are actually going to have some interface
Mm-hmm.
changes or something that is going to perform better. So I just have a question that, yeah, this point is right that you cannot control it.
Mm-hmm.
The defects you cannot control. But when you're doing the other catalysis like photocatalytic or thermocatalytic, then also until the mechanism is unveiled, you cannot tell everything, right?
Mm-hmm.
So, but this point I'm not sure here that the surface defects is a problem because we are doing this.
No, I would like to say, like in my presentation I was talking about like how surface defects create like more efficiency. I was not talking about like the problem related like which here I am discussing. Like I cannot control the amount of surface defects. Like if I am using plasma technology, it can create much, like sometimes it may create large amount of surface defects, or it may destroy the material's property. That's what the I want to discuss here. Not like the surface defects reduces or reduces the efficiency. That's what not the concern. I'm much more focused on like these surface defects I cannot control in this technology. Yeah. So yeah, this was my point. Yes, like it's not like only particular application. Like plasma, I am currently I like as I said, like when a material is being used, it can be used for different application. Like I talked about hydrogen and oxygen evolution, and also those materials can be used for lithium and batteries, and those materials property can be increased by plasma etching, or when we say the surface treatment of those materials by using plasma technology. So these defects don't have any application. Rather, I can say like the materials have different application, and their applications efficiency can be increased by surface treatment of those materials.
Yeah, I think the one issue is you still have controls because people don't understand how the plasma interact with whatever surface. If you have a more understanding those interactions,
then probably you can control, for example, defect as your type of defect, or what type of plasma, how, you know, or what plasma property, will affect those defect density type of defect, and where the defect. Because they, for your talk, you just said you just use plasma. Do they have any study on change the plasma property or study what the how plasma create those defects? What's the effect? You mean the basic mechanism? Yeah, the mechanism. Basic mech. Yeah, yeah. So like, oh, sorry. Yeah, as I like talked in my all these slides, like this like in I have just overviewed, or I have just talked about like how this, like what kind of defects that are being created by using plasma technology. And for, I haven't like yeah. What species in the plasma interact with your surface material, or the 1D or 2D material, how, what happened, and why those defects show up. Okay, no, professor. Like I'm not aware of it. Like I don't work on like purely. Yeah, 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 yeah. Yes, yes, yes. I understand. Integrate circuits. Basically, they spend a lot of time to or a lot of effort to understand it. Okay. One more thing is that, for example, in this slide, all those pictures from reference, right? I don't have citation. Like these pictures I took from. Oh, okay, okay, okay. Otherwise, it's not. Like I used these references, like yeah. From which slide? From which reference? Okay, I understand. Yes, professor, I can. That's important. So, okay, I think we don't have much time. Okay, you spent our time already. Thank you. Yeah, thanks. Okay.